Hello, in this video tutorial, we will be looking at derivation practice, that is deriving expressions for indicated variables. Practice for the AP Physics 1 and AP Physics C exams. In this video, we're going to be focusing on problem number 7. Please remember to pause or rewind the video as needed. Always remember to list any and all concepts before you begin. Read along with me, please. Planet X, which has a mass m, orbits a star of mass big M with a speed v in a circular orbit. Derive an expression for the radius of the orbit in terms of mass of the planet, little m, mass of the star, big M, the speed, and fundamental constants. Well, right off the bat, we know that there is a mutual attraction here, okay, of star and planet. So one main concept here should be viewed as universal gravitation. Okay, however, one thing that should also be noticed is that the gravity that the star is pulling the planet at any point around the orbit is always inward, pointing into the center of the circle, meaning it is also a Newton's second law centripetal force concept as well. We can start this problem by actually writing the following sentence. Gravitational force is a centripetal force. Okay, now I'm going to highlight parts of this sentence as we go. So gravitational force, centripetal force, and I'll go ahead and highlight is too. So gravitational force, well, that's your gravitational force equation. So gravitational force equation would be F sub g, the gravitational force equal to big G, the gravity constant, times m1 times m2 over r squared. Your centripetal force equation is F is equal to mv squared over r. So we're just putting those two together. And we get G, I'm going to let mass of the satellite be m1 and mass of the star be m2. So G little m times big M over r squared equals, now we're using the centripetal force equation, and we get mv squared over r. So centripetal gravitational force is equals centripetal force. Okay, look at how everything is organized. Now, you should also notice that a couple things are about to happen. Little m is a factor on both sides and will cancel, and one factor of r will cancel on both sides. So this is going to neatly reduce itself to big G, which is the gravitational constant. That's your fundamental constant right there, gravitational constant, times big M, which is the mass of the star, divided by r equals v squared. Now you're trying to develop an expression for the radius of orbit. So let's go ahead and solve for r. If we can do that by doing a little switcheroo right there, and we get the radius is equal to gm over v squared. And before you finish, you just do a double check and make sure that the variables are acceptable. Is G acceptable? Yes, it's a fundamental constant. Is big M acceptable? Yes. Is V acceptable? Yes. In the next part, it said that planet Y has the same mass as planet X and is moving around in a circular orbit with the same star, around the same star with a speed of 5v. What is the ratio of the planet's Y's orbital radius to planet X's? Well, here is your radius expression, Okay, so the radius expression is r is equal to gm over v squared. And what that means is the radius is proportional to just m over v squared because g is a constant. Now, planet Y has the same mass, so I'm going to replace m with the number 1. But the speed is 5 times greater, so I'm going to replace that with the number 5. And the radius of planet Y's orbit, the ratio of planet Y's orbital radius would be 1/25th that of planet X. What that would mean is the radius would be 25 times smaller. Planet Z moves at the same speed in circular orbit around a star with twice the mass. Okay, so R is proportional to m over v squared. Well, planet Z moves at the same speed, so I'm going to put a 1 squared down here because the speed didn't change. But the star has twice the mass. So I'm going to replace m with the number 2. And so we get 2 over 1, which is 2. The ratio would be specifically 2 to 1. In other words, planet Z would be twice the orbital radius of planet X, twice as far. And then finally, it says a satellite with a much smaller mass than planet X is put into circular orbit around the star at the same speed. So it's got the same speed, but it's got a smaller mass. Okay. Now it says, will the orbital radius be larger, smaller, or the same, right? So again, orbital radius is proportional to mass over v squared. If the speed is the same and the star's mass is the same, well, orbital radius it's independent of satellite mass. Therefore, the orbital radius stays the same.